Let's continue with our mass spring damper analogy for the aerodynamics of a controlled single-joint robot. Design of the controller allows us to alter the spring K and damper B, and therefore how the error theta E evolves. We divide this second-order differential equation by the leading coefficient m to get this form, where the leading coefficient is 1. Assuming m, b, and k are all positive, the aerodynamics are stable and the error will decay to 0. For stable second-order differential equations, it's customary to define the natural frequency omega n to be equal to the square root of k over m and the damping ratio zeta to be b over 2 times the square root of km. Then we can rewrite the differential equation as theta e double dot plus 2 zeta omega n theta e dot plus omega n squared theta e equals 0. This is the standard form for a stable second-order homogeneous linear differential equation. The characteristic equation of this differential equation is the quadratic equation s squared plus 2 zeta omega n s plus omega n squared equals 0. The roots of this quadratic equation are minus zeta omega n plus or minus omega n times the square root of zeta squared minus 1. Since zeta and omega n are real numbers, the two roots are real values if the quantity inside the square root is greater than or equal to 0. In other words, S1 and S2 are real numbers if the damping ratio zeta is greater than or equal to 1. If zeta is less than 1, the square root produces an imaginary number and the roots are complex conjugates. We'll consider 3 cases depending on the damping ratio zeta. If the damping ratio zeta is greater than 1, we say that the aerodynamics are overdamped. If zeta is equal to 1, the aerodynamics are critically damped. Finally, if zeta is less than 1, the aerodynamics are underdamped. Let's look at the details of the error response for each of these cases. First, for the overdamped case, the error response that solves the differential equation is the sum of 2 decaying exponentials, where the roots S1 and S2 are shown here. We can plot the roots in the complex plane defined by the real and imaginary axes. Since the aerodynamics are stable, the roots have a negative real component and therefore lie in the left half plane. Since these roots are real numbers, they lie on the real axis. The time constants of the 2 corresponding decaying exponentials are the negative inverses of S1 and S2. We can plot the unit step error response by solving for C1 and C2 using the initial conditions theta e equal to 1 and theta e dot equal to 0. The sum of the 2 decaying exponentials tends to be dominated by the exponential corresponding to the less negative root. We call this the slow root, since its exponential decays more slowly. If the aerodynamics are critically damped, then the roots are identical at minus omega n, and the error response takes this form, where the time constant of the decaying exponential is 1 over omega n. Solving for C1 and C2, the unit step error response looks like this. Again, there is no overshoot or oscillation. Unlike the overdamped response, neither of the roots is slower than the other. As with the first order response, the 2% settling time is approximately 4 times the time constant of the exponential. Finally, the aerodynamics are underdamped if the damping ratio is less than 1. In this case, the error response is a decaying sinusoid. The time constant of the decay is 1 over zeta omega n. The frequency of the sinusoid is the damped natural frequency omega d, which equals the natural frequency times the square root of 1 minus zeta squared. The roots are complex conjugates with a real value minus zeta omega n and an imaginary value plus or minus j omega d. This is the unit step error response. The 2% settling time is approximately 4 time constants. We can calculate the overshoot as e to the minus pi zeta over the square root of 1 minus zeta squared and then express it as a percentage. Plotting the responses on top of each other, we see that if the 2 roots are complex conjugates in the left half plane, we get an underdamped decaying sinusoidal error response. If the 2 roots are real but not equal, we get an overdamped response dominated by the slow root. If the 2 roots are coincident, we get a critically damped response, which in this case converges faster to 0 than the overdamped response because the roots are faster than the slow root of the overdamped response. In summary, if any of the roots lie in the right half plane, the controlled system is unstable, and the error grows exponentially at a rate that increases the further the root is to the right. Similarly, the further the roots are to the left, the faster the error decays. Finally, if the roots are not on the real axis, the error response will exhibit overshoot and oscillation that increases with the imaginary components of the roots. These observations hold for higher order systems too. The more negative the real portions of the roots of the characteristic equation, the faster any initial error decays. In the next video, we'll finally begin applying what we've learned about linear error responses to the control of a robot.